A'udhu billahi minash shaitanir rajeem. Bismillahir rahmanir rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Hello and hi world. Very good morning, good afternoon, and good evening. Ladies and gentlemen, I am Mohammad Johar Islam, postgraduate research student, Advanced Lightning and Power Energy Research, ALPAR UPM, and I will be moderating this session. I feel privileged to extend my warm welcome to all presented here and registered to our today's webinar entitled Solar Renewable Energy Challenges and Opportunities. This program is organized by IEEE University Putra Malaysia student branch in collaborations with IEEE Power and Energy Society Malaysia chapter, Advanced Lightning and Power Energy Research ALPA UPM, IEEE Malaysia section, and IEEE Women in Engineering, marking the IEEE PES Day Celebration 2021. At the very beginning of our today's session, I would like to invite Mr. Isumullah bin Luqman from Malaysia to recite from the Holy Quran. Please welcome Mr. Isumullah bin Luqman.
Assalamualaikum warahmatullahi ta'ala wabarakatuh.
Salam.
Is it clear, my voice?
Yep.
Okay. أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. يا أيها الذين آمنوا كتب عليكم الصيام كما كتب على الذين من قبلكم لعلكم تتقون أياما معدودات فمن كان منكم مريضا أو على سفر فعدة من أيام أخر وعلى الذين يطيقونه فدية طعام مسكين فمن تطوع خيرا فهو خير له وأن تصوموا خير لكم إن كنتم تعلمون شهر رمضان الذي أنزل فيه القرآن هدى للناس وأنزل الفرقان هدى للناس وبينات من الهدى والفرقان فمن شهد منكم الشهر فليصمه ومن كان مريضا أو على سفر فعدة من أيام أخر يريد الله بكم اليسر ولا يريد بكم العسر ولتكملوا العدة ولتكبروا الله على ما هداكم ولعلكم تشكرون صدق الله العظيم.
Thank you, Mr. Isumullah bin Luqman, for the beautiful recitation. Islam makes it a religious duty upon Muslims to seek knowledge. Once again, I would like to welcome you all to our today's webinar. For your kind information, we have received around 450 registrations from 35 countries, and this program is being telecast by IEEE PES Malaysia Facebook and YouTube channel. I am overwhelmed to have you all in our session, and please share our YouTube and Facebook live link to your social media timeline so that maximum number of people benefited 28 IEEE PES Day events, celebrating by 19,000 participants, 582 lecturers, 278 PES Day events in 50 countries, and 82 IEEE section. At this stage, I request Associate Prof. TS IR Dr. Muhammad Lutfi bin Uthman, Advisor IEEE PES UPM Student Branch, to give a brief overview of IEEE and PES Malaysia section. Over to you, Prof.
Okay. Thank you very much, Brother Mazhur. Can you hear me?
Yeah.
Okay. All right.
Yes, Prof, you are clear.
Okay. All right. Thank you very much. Assalamualaikum warahmatullahi taala wabarakatuh, and very good morning. Thank you for having me to be sharing a little insight of our IEEE and specifically about the PES, Power Energy Society. So I'm just basically trying to give a little insight on what we, as we call it, IEEE EPS all about, and what we are doing, and what we, or rather where we are actually heading towards to. Okay, IEEE is a world's largest professional association advancing technology for humanity. So it has certain mission statement as well as a vision statement. So as for mission statement, it's stated that IEEE's core purpose, its core purpose is to simply foster technological innovation and excellence for the benefit of humanity. And the vision is simply that IEEE will be essential to the global technical community and to technical professionals everywhere, and be universally recognized for contributions of technology and of technical professionals in improving global conditions. Simply because of it's really it's a large community, it's a large professional association in its effort to advance the technology for humanity. So, of course, as you can see from this slide, it has quite a humongous global reach. We have a total of about 422,000 over members throughout the entire throughout these 160 countries, which bulk of the members, student members, totaling 123,000. And there have been annual conferences, almost like close to 2,000 number of conferences, and still going on. And there are a few more coming up. They have been planned in the future. And as far as its specialties, IEEE, it's a very, broad aspects as far as providing technical knowledge, where within IEEE we have 4.5 million technical documents. It's a huge amount of documents there, and over 200 top cited periodicals, including magazines, journals, and there are very active standards within IEEE itself, almost like 103,000. And there are altogether within IEEE umbrella about 49 technical societies. And of course, the mission of IEEE is to actually to be involved as much as possible with the social or societal engagement, where we have a very impactful activities. We have public policy engagement, we have global humanitarian efforts, education such as trainings, webinars like what we are having now. And of course, with those trainings, there are certifications awarded, accorded to participants. And of course, we are very much into looking at the ethical aspects of engineering and technological activities. PS is the largest, or rather the second largest technical society in the IEEE. Well, altogether there are 49 technical societies, wrongly stated here. It's 49 technical societies, where one of them is IEEE EPS itself, Power and Energy Society. And as I've mentioned earlier on, IEEE has come up with large volumes of IEEE standards, and almost like close to half of the standards are actually created by this PS society itself. It's quite large there. Okay, why is it important that we be members of IEEE Power and Energy Society? Of course, being members of IEEE PS, it helps us in many ways. You can grow and maintain your technical expertise because we'll be involved in many activities, and you'll be liaising and having close rapport with many professionals. So that in that way it would improve your expertise in that sense. And then you can, of course, get connected to other professionals, as I mentioned earlier on. You can contribute your expertise to the future of power and energy. And of course, being members, you will be offered with programs, with materials that are available and in a discounted price. Why being a PS member important? Because you, of course, can stay technically proficient. We have many online webinars, tutorials like what we are experiencing right now. We have on-site training workshops. We have practice-oriented technical journals, and we have plain talks, basic courses for those at entry levels, novice or newbies, we call it, new engineers, or even for, of course, senior professionals in the industries. So PS is simply trying to actually deploy significant resources for training and lifelong learning activities for our practicing engineer members. And many of these resources are eligible for continuing education units, which you can collect to certify your continuing practice as professionals in your own professions. And you can collect professional development hours for that purpose as well. As I mentioned, there is a resource center, as shown in the link there, IEEE EPS Resource Center. You can access to almost like 1,400 items. So this is simply the most extensive library of content in the world, devoted exclusively to the field of power energy. There are almost anything you can find through this link, things like tutorials, videos, technical reports, journal articles, archived webinars. So as you should have already understood, this webinar that we are having now will be archived later on. You can reach or access this recorded webinar later on, inshallah. And then there are conference slides and a whole lot more you can get from this resource center. And we mentioned earlier on about global engagement. We have local chapters. Each and every region has its own local chapters. We are now in Malaysia, of course, and we are in Region 10. There are altogether about 45 chapters, amounting to almost like 900, close to 9,335, close to 9,400 members is counting. And under this PS, we have almost altogether throughout the entire world about 38,600 members from almost like 150 countries. So altogether, there are 260 chapters. We have 421 student chapters, and where I'm from, UPM, we have our own chapter, UPM Student Branch Chapter. And PS chapters are a great way to plug into the society in most parts of the world and get involved. So of course, this is one of the ways that we're trying to serve the society by sharing knowledge from our two honorable professors that will be presenting their materials to you guys. And these are all our previous, as well as of course the current PS chairs. We have Prof. Hussein, the first one, then we have Prof. Norman, Prof. Emeritus, Dr. Azhar, Engineer Michael, and then Dr. Zahrul, Prof. Ismail Musirin, Prof. Izaham, Prof. Zainal, Prof. Zohaina, and then Dr. Fauzi, Engineer Yo, and of course currently in the helm is Prof. Hazli Mukhlis. So these are all the chairs you can see in the slide now. And what essentially we are doing, We have invited lecturers, we have conferences, we have awards for outstanding engineers. Of course, industry, we are very much engaged with the industries. We link ourselves with a lot of activities with industries. We have technical activities, and those students in the final year, they can be also awarded or delivered with awards if their final year projects merit such awards. And we do reach out to members. And one of the ways to actually reach out to members is actually to conduct a roadshow, or we call it a senior membership drive, where we conduct drives to get as many senior members as possible from the current pool of members. So let's become a member. For those who have not become a member, please be one. So first of all, you can be an IEEE member, and immediately after that, you can be a PS member as well, together at the same time. So there are, of course, many benefits you can benefit from being IEEE members, or specifically being a PS members, such as getting the magazines, journals, they are at a discounted price. But for the first year, for PS student especially, there is a free membership. But of course, this would valid for 1 year. And why is it important that you be a PS student member? Maybe I can just read out the list here, the benefits that you can gain from being PS student member. One is you can enjoy free subscription to PS award-winning Power Energy magazine, as I mentioned earlier on. You can gain free access to PS Resource Center, the library, the online library, Resource Center, with hundreds of technical reports, tutorial videos, and presentations. You can receive a free membership in your local PS chapter, all right? Receive discounted price on a whole lot of PS sponsored and co-sponsored conferences and meetings in our localities. You can take advantage of technical tutorials provided at the discounted prices. And you can also utilize what we call these PS carriers. It's actually a free service. It helps undergraduates or the graduate engineering students to connect with employers the world over, not necessarily in where we are now in Malaysia. So of course, this offer will only be valid for 1 year. And who has not been one, please be a member. Okay, right now there are many benefits you can get from. So I think that with that, please enjoy the presentation by our honorable two professors. I've provided this here, the link that you can link yourself to and get more information from IEEE, especially IEEE PS. So this is our lineup right now. We have in our current IEEE PS Malaysia chapter. So with that, thank you very much, and I really appreciate your time and attention. So back over to Mr. Malzora.
Thank you, Prof, for all the insight of IEEE and IEEE PES. And I do believe that IEEE PES will contribute more to the advancement of technology for the betterment of entire humanity. Please subscribe our YouTube channel, IEEE PES Malaysia. So PES Day 2021 theme, the climate change is perhaps one of the largest problems humanity has faced, and our world is changing faster than ever, being the society that governs the engineering aspect of energy production that has resulted in greenhouse gases and global warming. And we must educate everyone on the solutions and technological developments that are happening to slow down this issue. And that's why this year the PES Day 2021 theme is Clean Energy Revolution. Therefore, we have invited two prominent researchers and academicians to our today's webinar who have been advocating a carbon-free society for all. Prof. Dato Dr. Kamaruzzaman Sopian obtained his BSc in Mechanical Engineering from the University of Wisconsin-Madison in 1985, MSc in Energy Resource from the University of Pittsburgh in 1989, and PhD in Mechanical Engineering from the Dragon Solar Laboratory, University of Miami in 1997. He is presently the officer in renewable energy at the Department of Mechanical and Material Engineering, University Kembangsaan, Malaysia. Currently, he is the director of the Solar Energy Research Institute, a center of excellence for the research and development in solar energy technology. He has been involved in the field of solar energy for more than 20 years, and his main contributions are in solar radiation modeling, alternative material for solar absorber, solar water heating system with integrated storage system, solar desalination, solar cooling, daylighting using solar light pipes, solar assisted drying system, and grid connected photovoltaic system, thin film silicon solar cells, combined photovoltaic thermal or hybrid collectors, and solar hydrogen production system. He has published over 400 research papers in journal and conference. He has delivered keynote speeches at national and international conference on renewable energy. He is the founding member of the Malaysian Institute of Energy, member of the World Renewable Energy Network based in the United Kingdom, and is an associate editor of Renewable Energy published by Elsevier Limited. He heads several national subcommittees on renewable energy by the Malaysian government to promote awareness, market enhancement, policy studies, and applications renewable energy. According to his Google Scholar account, his H index 89, I index 510, and his publications have received 30,821 citations. In recognition of exceptional research performance, he has been selected as highly cited researcher 2020. Congratulations, and please give a big hands for his wonderful achievement. As you all are eagerly awaiting to know more about the solar energy to have a carbon-free, better and safer world, I would not keep you waiting anymore. Directly, I'll go to Prof. Dato Dr. Kamaruzzaman Sopian to deliver his talk. Prof, the floor is yours.
Thank you very much. Thank you for the kind introduction. I will now share you my presentation. Can you see this? Can you see the presentation?
Yes, Prof, it's clear.
Okay, thank you very much. I will begin the presentation now. The title of my presentation today is on solar energy technology innovation for the low emission pathway. Now, I will within this 30 minutes, I will be presenting to you some aspects of carbon reduction, and in order to basically achieve this carbon reduction, I will pinpoint to you a few of the areas that I think that will have an impact and will require some sort of innovation, basically to achieve the low emission targets. And then I will conclude. Now, with respect to this, as you know that a transition between the environmental, the polluted fossil fuel to a low carbon economy requires the use of renewables, and it is expected that 2/3 of this can be covered by renewables in order to meet the emission reduction targeted emission reduction by 2050. In addition to that, we have a target of limiting the increase in temperature due to climate change in less than 2 degrees. This particular diagram is actually, it shows you how much energy you basically need in order to get 90% reduction in terms of the carbon emission. In order to do that, by 2050, the gap between the energy consumption, energy production from fossil fuel will increase, and it is anticipated that you need about 200 etajoule of renewables to achieve 90%, basically 90% reduction in the carbon emission by the year 2050. So therefore, in order to look at that, so what sort of innovation you need basically to basically look into in order to fasten this carbon emission. I basically will divide into the classification of the innovations in terms of system operations. Number two, in terms of enabling infrastructure, followed by market regulation. Of course, some business models. So these are the area that I look into, and some sort of, a lot of innovation basically can be done in this area in order to meet this carbon reduction. In terms of the system operation, the innovation trends in future power production include digitization, and of course we have heard of this energy 4.0 with respect to the energy 4.0, the industrial revolution 4.0, and the use of big data and so forth will be a major area in digitalization. The system of the future will be decentralized. It will be more flexible. And of course, the electrification is at we're looking into at the end use of it. And going into flexible energy systems, the concept is that you accommodate the largest possible share of the various renewables, such as solar, wind, or even biomass, for that matter, in this flexible energy system. So there will be innovation in this field, and there's a lot of research opportunity also in this field. And another concept is what is known as the net neutral renewable energy community. This concept of net neutral community is a concept whereby a community, a township, a city, or a state, or even a country is energy neutral. Basically, if in an annual basis, the net import is not necessary from outside those particular communities, district, or state, or the offset of the energy conservation is actually done within the district itself. So this capital concept will then go into the concept of the zero energy building, zero energy community, and so forth. A community is net neutral when you have all this renewable energy being used in your particular location of your communities. We, on a small basis, we have done one simple net neutral community, renewable energy community, in one of the Orang Asli community in Pahang. We have installed this particular system that basically covers the energy needs for a community of 5 families, and they basically energy is delivered to them. They can also use it basically for income generation and so forth. Low energy house, for instance, is a major contributor to this net neutral community. The use of renewable energy features, technologies, as well as energy efficiency is particularly important for looking into the perspective of low energy building. So therefore, you can see the concept of low energy building, the concept of ultra low energy building, and then the concept of later on for net zero energy building. This is one of our design of a low energy building that we have installed in UKM. And the measure for low energy building is by the use of the building energy index. Your building energy index is the energy required per meter square of occupied space per year. And this is the important index. If you look at commercial complexes, it's about 300. If you look at hospitals, it's more than 300. Buildings are going towards the less than 100 BEI, building energy index. In addition to that, in terms of enabling infrastructure, the use of your artificial intelligence and the Internet of Things, basically to look into the energy consumption of a city. This is an example of the island of Pulau Pinang, whereby you can basically pinpoint which building is actually using a lot of energy, and therefore energy conservation measures can be conducted. In addition to that, you can have virtual energy audits to be done. This is an example of a building which through the use of this particular software that you can basically look into energy that basically uses a lot of energy. As I said earlier, more of in the future, we are looking into more of virtual energy audits instead of the physically energy audit that is done by energy auditors. But verification is also needed. In addition to that, the concept of smart cities and so forth, and now this artificial intelligence and internets of things, or even internets of everything. And now we go back into some of the innovation, for example, in solar collectors, solar panels. Now, one of the aspect of solar panels is that the cost of the solar panel has reduced from $50 per watt in the 50s to 40 cents per watt today. So there are a lot of reduction, the cost reduction. The cost reduction is mainly because of the economics of scale. Number two, because of processing, because of advances in manufacturing and so forth. Yeah. But it means that the price of the solar panel is getting cheaper and cheaper every year. But the most, if you look into the process of making the solar panels, there are a lot of materials that you can consider to be hazardous, to be considered flammable, that is basically used in the process of making those panels. In the conventional process of making the silicon solar panels, and of course there are variation of the process depending on what you are doing. There are also back contact solar panels. There are also the various types of solar panels, bifacial and so forth. But the process of making it is basically the same. It goes through a process of wet chemical etching, alkaline texturing and so forth. And then during the emission of the emitters, those grids that you see on the solar panels, this requires flammable material to do it. And you basically can, these are the toxic and flammable material that is used in making the solar cell. But you basically can, go through a process whereby you don't have to use them. There are advances in basically looking into dry texturing process. There are advances in basically not using silane for the anti-reflective coating. You can use the silicon oxide itself as the coating for it. Of course, this basically will result in lesser processing steps, but also you cannot. In addition to that, you don't compromise on the efficiency of the solar cell. So the way forward basically for this is basically to go into a more environment friendly and cost competitive solar technology for it. And of course, if we look into some of the advances in tandem solar cell, the use of perovskite, silicon, and so forth, you can see that these are going towards the higher efficiency solar cell, even to the 45% efficiency solar cell. Now, if you in the 90s, it was said that if you can go to a cheaper solar panel with less efficiency, you are okay. But now, if you go to a 45% or beyond the 30% solar panel, or beyond the 25% solar panel, for that matter, you can see that the energy payback period for that panel will be lesser, compared to those solar panels that have lower efficiency and lower cost. So therefore, there is the way forward, mainly for future solar panels, is basically looking into high efficiency solar cell. There is also a type of solar panels, the type of technology they call photovoltaic thermal collector. In this particular solar collector, you basically will go into collectors that will produce heat and electricity simultaneously. Therefore, you will be saving space, you'll be saving, the system will be more compact, and you have generation of also heat and electricity simultaneously from one compact unit. Now, this is an example of solar photovoltaic thermal collectors. The design of the solar, if you look into the operation of these solar panels, the temperature of the solar panel can easily reach a temperature about 50 degrees to 55 degrees. So therefore, it is actually prudent, basically, for you to get the heat out of it. And basically, when you can get the heat out of it, you'll be able to basically have a more efficient system. And here are example of the use of nanofluids, basically to enhance the heat transfer, basically to get more output from a solar panel. Therefore, a solar panel which actually operates at about maybe at about 14 to 18% will have an increase in about 30% from its present power by the use of fluids that is basically used to cool down the system. And also the addition of the nanoparticles and nanofluids within the system will enhance the heat transfer. You can also have, in the future, a system that basically also generate electricity and also generate hot water into the particular housing unit. And this will basically pave way for a system which is basically more compact and also multi-use and also savings in energy. Again, the solar we don't have to think solar of just what we call producing electricity. Energy is not only in the form of electricity, energy also is in the form of heat. So therefore, you can see a lot of application and a lot of energy is used basically in the low to medium industrial process heat application, such as the space heating, for space cooling, for drying, and also for industrial process heat. This particular picture is a picture of one of our units in the UKM hospital, basically for generating hot water for the hospitals. If you look into the way forward into these photovoltaic panels, you can see that most of the applications are actually more widely used, and it can be incorporated in the built environment, it can be incorporated in industry, and so forth. Now, the talk of the many of the renewable energy proponents is the hydrogen economy. Now, what is a hydrogen economy? In the hydrogen economy, primary energy sources like solar, like nuclear, like even biomass, and even the fossil fuel is used to produce hydrogen. And the hydrogen is not the fuel. The hydrogen is the energy carrier. And it can be used in the electricity sector, in the transportation sector, as well as the residential, commercial, and also the industrial sector. Now, if you look into the rationale behind it, in a normal system, in a normal power station, if you use coal, the efficiency of the solar thermal system, the efficiency of the coal power generation system is about 38%. By using hydrogen as the energy carrier, the overall efficiency of the system is about 42%. So the benefit of it is that it's cheaper transportation, it's more energy, more environment friendly. So there are a lot of this concept on the hydrogen infrastructure and so forth. Yeah? And even Malaysia is also looking into the hydrogen roadmap for the future. Yeah? And it's not only Malaysia. If you look into some of the countries in the world, the advanced country in the world, they are also looking into this concept of the hydrogen economy. Now, we We have done, in our part, we have done small study before, and we call it solar hydrogen Ecohorse. We have solar basically running in a fuel cell, and the fuel cell basically produces hydrogen, and the hydrogen is actually stored and basically used later to run the fuel cell. In addition to that, the system is grid connected. Therefore, when times you already you have the hydrogen filled up, you can use you can send the excess electricity to the grid. This is our system in UKM. In addition to that, this in terms of business model, this is now in terms of the business model. You look into what is known as the blockchain. Now, in this case, you can see that the excess electricity that is generated, it can also be exported and can also be imported. Now you have that system in Malaysia, but you have to have a platform basically to enhance it, to enhance communication between house to house, so that the house and the house can sell each other instead of going to the grid. They can sell it, and this can be done by using the blockchain-based network security systems structures. This is an old system. It's called in terms of market regulation. Malaysia has this feed-in tariff, but this particular policy is already it's not there anymore. In any new if you want to go into this, let's say, business of promoting the use of grid-connected renewable, the best is go to feed-in tariff. But feed-in tariff requires a parliamentary act. So therefore, we have passed through this act. We have been operating the feed-in tariff since 2011, I'm not mistaken, and we have the last of it was 5 years later. So what it means is that if you have a system of renewable system on your roof, by law, with terms and conditions, of course, that you can sell it to the utility. The utility will buy you at a very premium price, but that is within certain period. The reason the reason for it is basically to enhance the market for it. But because you cannot, because this is actually a sort of a subsidy program. The next would be this what do you call it, the net metering system. And of course, the net metering system now, in Malaysia, we have the NEMS 3.0, and the NEMS 3.0, if I'm not mistaken, please correct me about this, is that there are three incentives. Number one is the NEMS for the rakyat, or the NEM for the public, which actually having a 4 to 5 kilowatt system on top of your roof. Number two is the NEMS for the government of buildings, and of course, NEMS, the net energy metering for basically the private companies, for example, shopping complexes and hospitals and so forth. We have another scheme called the self-energy consumption, which is basically a self-consumption program. Whatever you use, whatever you generate, you use it. For the NEMS, you can basically deliver the energy to the utility. And this is actually the just to show you. This is you look into. This is my house actually. I'm still under the feed-in tariff for RM1. I generate about. I have a 7.5 kilowatt system that I basically generate to the grid at RM1 per kilowatt hour. So it's quite attractive. At the time, the system is no more there. So I'm basically getting about maybe RM700 per month from this. So I've said many times that I have two jobs now. Number one, I'm teaching. Number two, I'm also exporting electricity to the grid. You can also have program whereby you share roof. In some countries, you have the share roof program. And I've shown to you how the innovation basically in the use of renewables, basically in the system operation, in the infrastructure, as well as the market regulation, and some very innovative business model that basically can be used to fasten the the carbon emission till 2050. To conclude, I would like to show you some of this particular roadmap that I basically think will contribute basically towards the low emission targets by 2050. By 2020 till 2025, we should basically accelerate to have more environmentally friendly products, systems, and processes, and so forth, decentralized systems, and so forth. Go for energy efficiency, go for this renewable energy, so forth, and then it should be more destructive. It's more destructive towards the 2030, where we go into transitions towards the hydrogen economy, the use of smart grids, and more decentralized systems, more power independence, more democratization of the use of electricity. And finally, with the 2050, not only solar, you're also looking into wind, nuclear, biomass, solar, geothermal, OTAC, wave, and these are the energy. They are not in competition to each other. I'm not proposing only solar. You also need to look into other form of renewable energy, other form of carbon-free technology, that will basically have an impact towards the targets of carbon emission towards 2050. With that, I would like to thank you, and I'm happy to take any question after the presentation. Thank you very much.
Thank you, Prof, for all the insights on innovations in renewable energy. To those who just joined, we have over 450 registrations from 35 countries, and the attendance form has already given in the comment section. If you have anything to ask to our honorable speakers, please write in the comment below. So now we'll go to our second speaker of today's session, Professor Dr. Nowshad Amin, who is originally from Bangladesh. His nickname is Shabuj. In Bengali, it means green. His hometown is also a greenest one called Chittagong. With all the coincidence of green in life, he is a great fan of green technology and enthusiastic promoter as well. And he wishes to be a green citizen of a greener world. So Dr. Nowshad Amin is currently serving as a professor at the College of Engineering of the University Tengah Nationals, that is called UNITEN of Malaysia. Prior to this, he served over 11 years in the Department of Electrical and Electronic Engineering and System Engineering of University Kebangsaan, Malaysia, where he also led the Solar Photovoltaic Research Group under the Solar Energy Research Institute until January 2018. He also served as the visiting professor at the King Saud University of Saudi Arabia from 2010 till 2015. After completing the higher secondary education from his native country, Bangladesh, he received Japanese Ministry of Education Monbuso Scholarship to pursue a diploma in the electrical engineering in 1994 at Gunna National College of Technology. Bachelor's in Electrical and Electronic Engineering 1996 at Tohiasi University of Technology, and then Master's 1998 and PhD 2001 in Solar Photovoltaic Technology at Tokyo Institute of Technology, Japan. His areas of expertise include microelectronics, renewable energy, solar photovoltaic technologies, and thin film solar PV development. His research entities. He served as the CTO of University spin-off company financed by the Malaysian Technology Development Center, MTDC. He has been serving as the principal investigator and principal investigator of many government and international funded projects. He has authored more than 350 peer-reviewed publications, a few books and book chapters. He is actually involved in promoting renewable energy to the developing countries in South and Southeast Asia and working as an enthusiastic promoter for the affordable renewable energy resources. According to his Google Scholar account, his H index 35, I-10 index 151, and his publications has received 5,723 citations. He is one of the top 11 scientists in Malaysia under applied physics in 2019. Congratulations, Prof. Without further delay, I would like to invite Prof. Nowshad Amin to present his talk on prospects and challenge in solar photovoltaic technology. Please welcome Prof. Dr. Nowshad Amin. Over to you, Prof.
Thank you, Zuhrul, for a very benevolent and generous introduction. It was too long. I was really tired of listening to it. Anyway, let me share my screen first. Can you see the screen?
Yes, Prof.
Okay. Once again, thank you, IEEE PES UPM Malaysia, for inviting me to share my experiences on thin film photovoltaics or photovoltaics as a whole. My name is Nowshad Amin. I'm working as a professor in the College of Engineering, and also I have been seconded to the Institute of Sustainable Energy to look after the research R&D in the solar PV. Okay. First, before I start, let me express my deepest condolences to those who lost their nears and dears amid this pandemic, and also who are fighting now, and also helping us to fight against this pandemic round the clock, round the world. I belong to UNITEN, which is in English the National Energy University, and the campus is in Putrajaya. Those who are not familiar with UNITEN, it is in fact energy-related, energy-focused university in Malaysia, under Tenaga Nasional Berhad, which is a power utility company. I'm very grateful that IEEE PES Malaysia UPM invited me and to have a session with Prof. Dato Kamaruzzaman, and he is one of my mentors in Malaysia, and I'm really happy that to be. I'm really happy to be with him today and share our experiences. Now, let me introduce a little bit about our UNITEN's effort in research related to energy. We have, apart from teaching under 3 different colleges, College of Engineering, College of IT, and College of Business Administration, we are also having 5 research institutes, namely Institute of Power Engineering, Institute of Sustainable Energy, etc., etc. So this one, the middle one, I belong to this one, to look after the research on solar energy. So in our ISC, or Institute of Sustainable Energy, we in fact focus on 5 different aspects, like, for example, as you see, biofuel, then hybrid renewable energy systems, wind, and sustainability issues. So we have main is solar. And as I mentioned, that I joined after UKM in 2018 as an advisor to this ISC, especially for the solar. Then I created the group called Solar PV R&D Group, research group, or unit, where we have a clear vision of focusing on solar PV related research. We have these missions. I don't read out everything, but our clear vision is to excel in R&D, especially in solar and solar related applications. The unit is quite big. We have 7 wings, I should say, 7 wings or 7 subgroups under this unit. I'm heading this one. So I have classified into different aspects of solar energy. For example, first of all, we do research on fundamental things, and the second one is we also do research on applications. We have almost 35 members, active members now, with 27 million Malaysian ringgit equivalent research funding at present. So we have generation-based research activity on solar PV, as well as we have some material science research besides this application-based research. I would like to acknowledge my whole group. This is a part of the group where we meet almost every week. Even it is virtual, we meet every week, and Monday afternoon is our meeting time for 2 to 3 hours, is usually in the afternoon. discuss about our research progress and everything. I would like to acknowledge the funding agencies like MOSTI of Malaysia, apart from other collaborators around the world. So today's outline is, I have already introduced myself and our entity, the UNITEN, and you can see a picture of the whole university at a glance, bird's eye view. And after my introduction, I'll be touching the solar PV. Prof. Dato Kamaruzzaman has already talked about the overall aspects of energy, PV, and other aspects of renewable energy in the economy, in sustainability. I'll be focusing on, especially on the scientific aspect, like especially on the technological side, and focusing only on solar PV, because this is the field that I know. I don't know much about others and about the solar PV technologies beyond us, because we don't do everything. It has so many different aspects, so many different interesting topics. So after that, I'll be touching the challenges and prospects. I mean, there is challenge, of course, and there's also prospect, future prospect, how to overcome those challenges. So those things will be discussed. And finally, I'll try to conclude as a way forward thing. So just to remind you about the solar PV, what is solar PV? We say solar photovoltaic. Okay, so what is that? So in fact, there is a device called solar cell. This solar cell is exploiting or utilizing the solar photovoltaic effect of some specialized materials and under some device configuration to produce electricity directly from sunlight. So that is the main thing, that we produce electricity from sunlight using the solar photovoltaic cells. And it is silent. It doesn't produce any kind of emission, polluting gas like SOx or NOx, etc., carbon monoxide, carbon dioxide, while it is producing electricity. And one of the interesting thing is just it's very thin. Like you don't need that much materials, only roughly from, let's say, 200 micron to way down to 2 or 3 micron thickness of this special device can produce electricity up to megawatt range or gigawatt range nowadays. So it's in fact, electronic device, which is a PN junction, as you can see, cross-section of a solar cell, typical solar cell, silicon-based solar cell. Light comes from the top side, and then light is absorbed in the junction area, and there are carriers produced, and the carriers is being collected, are being collected through the terminals to use in the load, different kind of loads. This is the basic concept of solar cell. And if you want to look into deep, this is a kind of PN junction where we have a P-type and N-type polarity materials, usually called P-type semiconductor and N-type semiconductor. Then it creates, whenever light is absorbed, the electrons or carriers are energized and which can be extracted out through the terminals. And how do we measure the efficiency? We just take the P out, power out, over power in. Power in is constant because we get how much power or energy from the sun. We already know there is an average figure. About the power out, it depends on the different kind of configuration of the solar cells and different kind of technologies and different kind of ability, etc., etc. So this is the variable here. So it is the deciding factor for the conversion efficiency. Usually the conversion efficiency for any terrestrial solar cells are roughly below around 25%. That means out of 100% light, 25% can be extracted efficiently outside. And one of the other advantages of solar cells are they can be made as rigid as you see nowadays, or it can be made flexible. It can be made transparent, semi-transparent, etc., etc. So it's the beauty of this technology that we can make in different ways according to our needs. A little bit of the historical pathways of solar cells. This photovoltaic effect was discovered by Edmond Becquerel, a French physicist, almost 200 years ago, 180 years ago. After that, there has been little progress until 1941, whenever the first silicon-based solar cell was reported. Then finally, in 1954, almost 70 years ago, we got the efficient, like we can call it reasonably efficient solar cell, was invented by three researchers from Bell Lab, as you can see the figure here. So I'd like to stress a little bit on that because it's a PN junction, as I mentioned before, that is an N-type semiconductor is covered by the P-type materials. It can be doped or it can be diffused, or there can be another layer, etc. And we need just a terminal to take out the carriers. So the first solar cell, as you can see, I got the picture from some of our collaborators that the first solar cell is still, it is somewhere in Bell Lab in their museum to show, and that time it was 6% efficiency, and they measured the efficiency in 2002. 2002, you can see the date here. Still, the efficiency is showing 1.54%, but that means it deteriorated, but it still is showing 25% of the original efficiency of 6%. So it's quite reliable. Even after 50 years, the solar cell is still alive and it is still serving, but there is some deterioration. So this was the tremendous step that mankind has taken, I should say, around that time. So that means we don't need to burn any fossil fuels to create electricity. We can just simply put some panels towards the sun and we can enjoy the electricity for free. So I always show this one. I still have this calculator. If the camera is open, you can see this calculator in my hand. So I purchased this when I started my education in Japan in 1990. I purchased this one in 1992, which has a solar panel here. And later on, I came to know that this is amorphous silicon-based solar cell, and it was in milliwatt peak range. And this solar cell does not need any battery. Even I use after now is almost 30 years, right? There's no battery on backside, but still in the light you can see that there's some figures, right? So still, this solar cell of that year's technology is still alive. It's still serving my purpose. So it's a tremendous thing that I really enjoy nowadays. So how big it can be? It was in milliwatt peak range, but it can be up to 400 watt peak range. That means, I mean, if you add the wattage or capacity of the solar cell, it is the unit we use. So it can be as big as 400 watt peak that 4% has to hold it, as you can see in this picture. But recently the development has go beyond, and now the biggest solar panel can be up to 460. We can make it much bigger, but there is a problem with carrying the solar panels by single hand. So that's the thing, that whenever we install, we need to make sure that the solar panel can be handled by preferably single hand, a single person. So we do not make it 1,000 watt in one piece, but we can add more pieces and to make it much larger. So what is essential for ideal solar cell? So I just put general criteria, like for example, the solar cell or solar panel should be cheaper, simple, and it should have abundant material, so that we don't need to worry about the material supply. That it should have integrated large-scale manufacturability, so that it has this economical impact in manufacturing and it can reduce the price. Then cost, durability, recyclability, all those things should be also easier. In terms of materials and devices, the solar cell materials cannot be everything. The material should be a light absorbing material, and the light absorption coefficient should be over 10 to the power 5 per centimeter. And then it should have junction formation ability, usually first and second and third generation solar cells, which we use PN junction based one. We need that junction formation ability, and high conversion efficiency. That means a light to electron, okay, photon to electron conversion efficiency, we call quantum efficiency, should be higher, etc., etc. And in terms of manufacturability, yes, we have to make bigger in single piece. We have to make uniform. We have to make lighter. So these things are really concerns, or these are the things, food for thoughts for the research community even today. Even the materials are, for example, even I said the materials should be abundant and materials should be highly absorbent. But there are materials which has high absorption, but that is not matching with the solar spectrum. This is the solar spectrum in yellow curve. So solar spectrum is not uniform throughout this wavelength. So we have to make sure that there is a good matching between the absorption curve of any material and the solar spectrum. So whenever we do research, we must take into account that the materials that we'll be researching should have overlapping or best matching with the solar spectrum. So solar cell R&D needs knowledge about materials, definitely, and we have different kind of materials: inorganic, organic, bulk, thin film, dye. We need to know about the fabrication process, because any solar cell can be made into different kind of structures, like homo structure, heterostructure, MI, Schottky, etc. And also every materials can be deposited, can be formed, can be can be put put together to make the structure in different ways. So there are so many combinations, in fact. So that's why it's very interesting. That's why it's never-ending story kind of thing. And also, finally, even though we make a very good solar cell, does not mean that it will be in the market, because we must think about the economics of this solar cell for marketability. Because if I make a solar cell that is expensive, and you may not see is in the market. So there are so many research going on. That's why we don't see everything in the market today. Okay, today's technology, solar cell technologies, I'm including not only solar cell, but also its application here. So we can see different categories here. First of all, solar cell, let's say technologies or solar cell itself can be categorized into 3 different generations. For example, first generation is crystalline silicon-based solar cell, roughly 200 to 500 micron thick. These 2, mono and poly. Then second generation solar cells are very thin. It's 1/100th thickness of first generation, like roughly 1 to 10 micron. And we can see some different materials, binary semiconductor materials like cadmium telluride, and also amorphous silicon, and then copper, indium, gallium selenide, which can be put on top of glass, polymer, or even stainless steel sheets or metal foils. Third generation solar cell, there are many different aspects or many different kinds. Out of that, we can say there is multi junctions, or even perovskite, a new kind of material which has revolutionized the whole PV community, in fact, in the last 10 years. And apart from that, we have also PV applications like controllers, systems, grids, then BOS, we call it balance of systems, etc., etc. Our current research focus is like this. I have encircled all those research interests of our lab. Solar cells, there's solar panels. I should not say cell, we should say panels, because cells are like individual identity, but whenever we put together and we make it marketly available, then it's called panel or module. So these solar modules or panels are marketly available, and you can see first generation crystalline silicon-based one, like this. You can see a small checks. Okay, so the other ones are like thin films. You can see as a whole. You can see just a simple piece of glass. You don't distinguish between the glass and the cell. So these are the second generations, like telluride, cadmium telluride, and copper, indium, gallium selenide based solar cells or panels that are markedly available now. But honestly speaking, the 90% of the solar panels that are produced last year are mainly based on monocrystalline, and only half, 7 to 8% solar panels are based on these 2. Next, I would like to talk about the status of the solar cells and their limitations, prospects, etc. Research fronts, so that you can understand. If you are a novice, you can think of your alignment towards solar PV research, so that you can start where the scopes are more concentrated. You can think of that way. The first, let me a little bit explain about the monocrystalline-based solar cells, because it is the base, it is the mother of everything. So every time I say my students, let's learn the crystalline silicon cell first, then let's learn other things. Because this is the one, whenever we teach through books also, we also always teach, we start teaching the silicon-based solar cells, because this is the first one. Then from there, the derivatives came, and we can now we can make different structures, different configurations, and even we can change materials, etc., etc. But this is still the mother of all solar cells. So as you can remember, that the first so-called reasonable efficient solar cell was 6% efficient solar cell. Back in 1954, it was invented. So it was this structure. And over the period of last 70 years, I should say, it came across many different variations, and with improved efficiency. People tried to change structure, tried to incorporate other supporting materials, but not the base materials. Base materials is still silicon. So it went through these processes, and finally, in almost 10 years ago, we got the highest efficient solar cell in these silicon materials, which is around 26.7%. So what else can be done? Because 26% is roughly the theoretical limit for silicon solar cells. So what else can be done? So the thing we have sorted that in I think this one of my students found that in latest 200 paper related to silicon, wafer silicon based or crystalline silicon based solar cells, mainly talking about the light management. Over 60% of them are talking about the light management. Some of them are talking about the material quality, like 25%, and then finally interfaces, because if you see the cross-section of the solar cell, it has the main material is like, for example, crystalline silicon. The wafer is the main observer, but we need some supporting layers. But they are very thin. If you compare this, it will be nanometer orders. So if it is micron, it will be nanometer orders. So this, and they have the interface. So interface defects. We have to talk about the defects. We have to manage the light because silicon cannot absorb the whole spectrum. There are some loss, reflection loss, some losses are transmission loss. So how to manage those light, incoming light from the sun, which is free. The more the light, the more the carriers generated, and then these carriers generated can be extracted, and if we can really collect it through proper management, then we can really get the highest efficient solar cell. So I should include my UCAM era. I worked there 11 years together with Prof. Dato Kamaruzzaman, and I should say we had a dream to have like labs, and then we really worked hard last 14 years. I think 2006 I started my career in UKM. So the first lab we got in 2008, I think, getting 8 million ringgit, so far I remember, from MOSTI that time to create a pre-commercialization lab. So the lab had all those facilities to create from wafer to panel. So solar cells, the first generation crystalline silicon solar cells, it starts from the solar cell, and then finally you can make the panel. And this is also a technology, paneling technology. So in the front-end process, that means to make the solar cell from a wafer, we need certain steps, like a few steps, until to measure the efficiency. And in the module making, like Dato Kamaruzzaman is holding one, he was very young that time. So this was, I think, one of the panels made in that facility back in the past. So we had those facilities in Malaysia to promote to promote people to establish paneling industry, at least, so that that we can at least entry in some way. Then, okay. Also recently, I think this is our another venture, which is very lavish, or very, I should say, very over optimistic idea that to have the ingot puller, so that we also know the know-how of how to make the raw materials from silicon ingots or from sand. So this is another adventurous research project under UKM, and also we are doing together. We are using some LRGS fund from Ministry of Higher Education. Recently got together. So this is the picture that I got. That we are able to pull the silicon ingot, and we can slice it to make the wafer. But there is, of course, there's many things are to be considered. For example, the purity, uniformity of the doping, etc., etc. This is the thing that we have to do research here. Apart from that, we also try to learn the light management from the leaves, natural leaves, which we call biomimetic study. Okay, this is the new thing that because solar cells and leaf are basically the same, because leaves getting the sunlight as their food, and solar cells is getting the sunlight to create electricity. So the surface structure, in terms of surface structure, we can really mimic, or we can really copy the leaves that has very good surface structure. Then we can, if we can replicate it, that will be the best achievement in terms of silicon light management. So we have tried back in the past. Okay, making our silicon wafer textured and putting some nanorods, etc., etc. So we got some achievement in that. The red one curve is the IV curve, or the efficiency curve, we can say. You can see the vertical axis is for current from the solar cell. At least you can see that it was 0.5 ampere for not, like, for example, only there was no texturization, or there's no light management. But if we do the light management, we can improve the efficiency, for example, from 5% to 8.5%, or we can increase the light. The light is directly related to the electricity, or the total current. So this is one of our achievement that we did. Also, recently we have we try to do something else. For example, crystalline silicon solar cells are now they are making. They are trying to to compensate the defects on both top and bottom surface. This is the wafer. Wafer has a lot of dangling mounts on the top surface and bottom surface, so we try to compensate those, introducing amorphous silicon layer. We call it heat silicon solar cell, and we have designed in our lab, and using my alma mater, Tokyo Institute of Technology, last year, I think end of 2019, we made the solar cell, and these are the solar cells using our design. And we found that, yes, there's a huge difference in terms of efficiency. From 10% efficiency, it increased to 16% efficiency by introducing some surface passivation layer on top and bottom side, both sides. So this is a new kind of solar cells, and Sanyo has already, Sanyo or Panasonic has already commercialized this kind of solar cells, and which is the efficiency in that case. Our cell is not optimized one, their cell is optimized. They made up to 22% efficiency in terms of panel. Now the second issue is about the thin film photovoltaics, which is the second generation solar cells. Thin films are very thin. If it is, if the silicon solar cell is 150 to 200 micron thick, then it will be 1 to 10 micron thick, because most of the thin film materials, they have high absorption coefficient. And one of the other advantages of thin films are they can be utilized in low light conditions. For example, I have shown you this amorphous silicon solar cell, right? It is working in LED lamp. The room I'm sitting now, it has only LED lamps. LED lamps have very light, less light intensity. Even under the LED lamps, it is working. So this is the advantage of the thin film materials. They can work at low light conditions as well as at high temperature conditions. This is another good advantage of thin film materials. Then let me show three of the thin film candidates. But our research focus is cadmium telluride. Mostly we put our strength, and CIGS we have started recently. I will show some of the things, and also amorphous silicon, not as an individual cell, but as a heat layer for crystalline silicon solar cells. Okay, our thin film journey started back in the UKM in 2007. I can show the lab was given to me from Dato Kamaruzzaman that time. That it was abandoned house, and then I started converting it. Then finally, within 3 years or 4 years, it got a clean room shape inside. You see the clean room inside where we need special attire. And my supervisor, Professor Makoto Konagai, who is a very renowned figure in the whole world in photovoltaics, he came down to see twice, in fact, to support our R&D activity. Anyway, this is a very small room, in fact, very small scale lab, but it has produced so many PhD holders, so many masters, and so many research collaborations. The lab, if you enter from the entrance, so you can see a lot of equipments. I think this is one of our achievements, that we established this lab using very small amount of research funding, not a big amount of money, like using FRGS, LRGS, all those things, and apart from our that time UKM's support, especially. And if you go in, there is a clean room entrance. You can see a whole lot of equipments for the thin film fabrication systems. Mainly, these are physical vapor deposition systems. For example, molecular beam epitaxy, sputtering, multi-gun sputtering. We have thermal evaporation, annealing system, sulfurization system, spin coater, etc., etc. But honestly speaking, this is enough for thin film research. If you see that way, and it has done so many things, but we cannot, honestly speaking, we need more investment in R&D, because if you see the good kind of research labs in the world has huge investment, in $1 billion investment to get a highly efficient solar cell. Anyway, recently TNB has given us in UNITEN 24 million ringgit almost 3 years ago. Still 3 more years to go. So using that budget, we have created another lab, which is also a clean room, which is much bigger in size, which has just been finished, in fact, and I can show you the inside. It has more sophisticated equipments, more contemporary equipments, okay, like MBE and others, like supporting equipments, all are there, and we have just recently commissioned everything. Now everything is functional. So we'll just, in no time, we'll be starting our research activity on thin films and material science related research together with UKM, because we are partnering, in fact, with UKM SERI for thin film research. And equipment-wise, we have this, and for even third generation solar cells, which is under one of my colleagues in UKM, we need less investment. In fact, if someone starts in making solar cells, they should they may start maybe if they have low budget, then they can start from here. So it needs only fume hood and few things that is most related to the chemical engineering or chemistry. So third generation solar cells, especially which is dealing with organics, etc., etc. For characterization, yes, we need common equipments. We need certain equipments for device characterization. For example, this one, LIV, light IV, light current and voltage measurement system under solar simulator, and also we need quantum efficiency measurement, and we need some of the materials related characterization equipment. Luckily, we have got under one roof now. So this is one of the things that in our new investment in UNITEN research or solar PV research under UNITEN, that we got under one roof. We got clean room. Beside that, we have a characterization room where we have everything, and we have some more, like for example, Raman and PL, all those things. So let me start a little bit of our thin film research activity. Our main strength is telluride, which is a binary semiconductor, which is the main absorber material of this kind of configuration. But we have options, or we have many different kinds of options to put the materials, to do processes, okay, to change the device configuration. So still we are continuing. Last 12 years we are continuing this research. And one of our achievement was 15% efficient solar cell under this kind of configurations, which is the IV is shown here, and quantum efficiency measurement or spectral response is shown here. However, to do more in this research, so we are trying to change the TCO materials, transparent conducting oxide materials. We try to change the window materials, which is N-type partner for these P-type materials. We try to incorporate some back surface field. The concept is taken from silicon. So these are the things that we always try continuously without any hesitation. We try to do everything. Even the solar cell may be 1% efficient, but we try to make a solar cell. We try to make a IV curve even in dark configuration or dark condition. So one of our achievements by one of our that time PhD students who achieved 10% efficiency. From this kind of this is the ACM picture that you can see. We introduced oxygenated cadmium sulfide to protect the interdiffusion from this layer to that layer. Then we successfully achieved that one. In fact, then we got 10% efficiency in very thin layer, 1 micron thick of telluride layer, which is extreme low. I also tried a different kind of doping, because cadmium telluride is a material, is a self-doping material. So we need to dope extrinsically. That's what we tried, putting some layer. And one of such is that we tried to put silver, sodium, and copper into this. And we tried with laser doping. So we found that if you dope with silver, the efficiency is not good. But if you dope with copper, this IV curve shows at least 14% efficiency in that range. So this is some of our achievements as well. Recently, we are trying to do cadmium telluride thin film solar cells on top of flexible glass. You can see the glass this is not a polymer. This is called flexible glass. We found that some glasses are as flexible as any polymer sheet. So we are now trying this one, but this glass has pros and cons. So we are trying to do our research by different fabrication process, either by RF sputtering or closed space sublimation process that we have in our lab. So the result I'm not showing, I'm just introducing. Then the second, the thin film solar cell is called copper indium gallium selenium solar cell, or CIGS in short form, which has this configuration with this thickness, as you can see here, which uses roughly less than 4 micron as a whole. And that means we can preserve the material. This is the beauty of thin film solar cells. But this solar cell, for which we are going to make next step, has advantage over crystalline silicon. So crystalline silicon needs so many steps, in fact. But this thin film CIS needs 1/3 less steps, fabrication steps. That means it's cost efficient than crystalline silicon. Crystalline silicon, yes, the raw materials is cheap, but the processing is really costly. But here the material cost is a little bit expensive. That's why there is something like you have to balance or you have to see which way you want to go. This CIGS solar cell has a short payback time. If you compare it monocrystalline, polycrystalline, CIGS solar cell has less than 1 year of energy payback time, and it is working better in high temperature environment. This is the data from somewhere. the real practical data given by Solar Frontier, one of the company that is producing CIS solar cell. And even for the shading effect, CIS solar cell has not that drastic decrease. It is it's linearly decreasing the efficiency. So this is also a good thing about this kind of solar cell. Apart from CIGS solar cell, we are also doing its cousin. For example, we call it CZTS solar cell. CZTS is a copper, zinc, tin sulfide, because CIGS solar cell is using indium and gallium, which are a little bit rare, a little bit expensive. So we try to replace it by zinc and tin. So in that case, we can successfully fabricate the solar cell in our research facility, and the efficiency we got is around 4%. Still, we are continuing our research with different kind of buffer or different kind of configuration in this material. Then we are also trying, we have tried to put that CZTS on top of flexible substrate. This is one of our example. So let me brief a little bit about the third generation options. Until first generation it was thought about only single junction. That means there will be only one PN junction, one P-type, one N-type. But in case we want to improve the efficiency further beyond the limit, it is proposed by Martin A. Green, one of the pioneers in crystalline silicon solar cells from University of New South Wales, Australia. He has introduced back in 2012 that if you want to go more, we need to increase the junctions. But that means we have to put the junctions in tandem or in vertical integration. So tandem 2, tandem 3, tandem 6. If you do that way, then we can improve the efficiency maybe up to 60%. And if you do some more, then it may go up to 74%. These are all theoretically, in fact, not yet achieved. Anyway, let me show some of the multi-junction solar cells configurations. Mostly they are using exotic materials like gallium arsenide. Gallium arsenide is one of the costliest material for PV. That's why we don't use gallium arsenide for terrestrial or on Earth applications. We usually use it for extraterrestrial applications or space applications because we can squeeze the space, and then the efficiency can go up to 40%. In fact, this is true, 40%. And in some cases, if you concentrate it, it can go up to 47%. And the other new excitonic cells or emerging cells are photochemical cell, dye-sensitive solar cells. But dye-sensitive solar cells, almost 10 years ago, it came into real attention. But later on, it was completely replaced by perovskite. That I'll tell you soon. Anyway, still they have research scopes. The perovskite has replaced everything, I should say, even including this inorganic solar cells like our crystalline silicon as well as thin films, because perovskite materials within 10 years, the efficiency jumped from roughly like 6 or 7% to now 22, 23% efficiency. If you do not consider about this reliability, for example, its degradation, it is one of the I think I should say pioneer materials in solar PV right now. And it has so many different configurations. So we try to make in different ways, superstrate, substrate configurations, and different materials, different HTM, whole transport material, electron transport material, even perovskite itself. We try to make it methyl amino, lead iodide, methyl amino, lead halide. I mean, there are different options we can do. So still, there are some room to go for us as well. So in our research facility, together with Japanese collaborators, we have made solar cells, which is almost 18% efficient using some nickel oxide HTL layer, whole transport layer. Then we are trying to do perovskite and silicon solar cells. I think Prof. Kamaruzzaman already mentioned that we have a LRGS project. We are now trying to make tandemizing or make the multi-junction with silicon and perovskite, because already we have some knowledge about perovskite by last 6 or 7 years, and silicon we have almost 15 years of knowledge of silicon. So we'll try next our tandemizing the silicon and perovskite in these configurations. We are not doing any kind of highly concentrated photovoltaics. That is, I mentioned before that gallium arsenide-based solar cells, but let me introduce a little bit of the scopes to work there. Concentrated solar cells, they need lens, in fact, to concentrate the sunlight so that one sunlight can be up to 100 sunlights, okay, 100 times concentrated. But the thing is, the material cannot last long. Any materials cannot be cannot endure that kind of heat. Only gallium arsenide can sustain those radiation. So there are scopes. If someone wants to study on concentrated solar cells, there are different approaches like intermediate band gap, and also silicon and T5 or gallium arsenide tandem, as well as normal tandem, like for example top, middle, and bottom cells based on gallium arsenide. So there is a prediction. There was a prediction, I think, almost 20 years ago, that how far can we go. The predictions are shown by the lines, like the solid lines, and the reality is shown by the dotted points for each technology. For example, crystalline silicon, almost it is following the trend and almost saturated, in fact, for single junction configuration. For CIGS also, I mean, it's roughly there. Thin film, other options, amorphous silicon also almost saturated, in fact. Dye sensitized, we do not see any kind of. So if I show you the efficiency evolution since 1976, so we can say that multi-junction solar cells have achieved 47% efficiency. Crystalline silicon has achieved 26% efficiency, over 26%. Then thin films, CIGS have achieved, they have achieved almost 23% efficiency. So these are the efficiency of each kind of solar cells. Each one has pros and cons in terms of difficulty in making them, or in terms of price or cost to make them. So how we achieve this? In fact, until now, we have tried to bridge between the theoretical efficiency limit and also process optimization. So this was the tricks until now. That process optimization has helped us, in fact, to achieve the theoretical, almost towards the theoretical limit. But in future, we may have to change this concept. And what about the difference between the cell and marketly available or commercially available the panels? You can see if the cell efficiency 26, panels are less than that, almost 10% or 20, sometimes 20% less than that. Okay, the efficiency. So there is a gap between the like small scale and large scale because of the uniformity, because of the fabrication techniques, etc., etc. So there is also a scope to work there, how to bridge the gap between the highest efficiency lab scale solar cell and commercial solar panels. And about the reliability issue, we know that most of the solar panels now available in the market, they promise the lifespan over 25 years in some cases 20 years. So let's say warranty. Some of the tier 1 manufacturers, that is good one manufacturers, they give warranty over 20 years or 25 years in some cases. What after that, in fact? We even see, this is one of our study, now we are doing this study, we recently got TNB grant to check the degradation of the solar panels in the field and see whether we can predict the solar panels, this degradation before it really fails, so that we can really change and can prevent the loss from the solar farms to the utility company, so that they will not be penalized for their promises. Okay, so we found that yes, there are so many failures may happen due to different kind of atmospheric conditions in different places. For example, in Malaysia, we are the first one to study these things, hopefully, and we have seen some of the common mistakes happen all over the world. So we are trying to gather what are the parameters that really promoted this kind of failures or degradation, and we try to see what happens in Malaysian environment. So this is also a research criteria, and also the after end of life modules. So how to recycle them? This is one of the issue, that you just cannot trash it everywhere. You have to recycle the materials. These are the exotic materials, very costly materials. So we have to recycle. And one of our collaboration with Thailand have successfully recycled most of the materials from perovskite solar cells in the cell, research scale cell. So we have recently published paper regarding the recycling as well. So, but in terms of silicon, we have already, some of the companies are already in commercial scale recycling plant, mostly in Europe. They are very strict on recycling the things. So they have very good, well-established recycling facilities for crystalline silicon-based solar cells. Let's look at the prospects of silicon of the solar PV around the world. So this is like year-wise PV capacity or installed capacity, how much we install on rooftops, on maybe large scale solar farms, etc. So the data shows that in 2090 we got almost 600 something, in fact, over 600 gigawatt peak. 1 gigawatt peak is 1 nuclear equivalent, production capacity or something like that. So means in 2019 itself, we replaced over 600 nuclear power plants. Otherwise, we had to see some alternatives, in fact. So this is the way that I always say. So the more solar panels we are installing, the more we are making ourselves less dependent on others like nuclear power plants, which is the quickest way to solve any electricity problem around the world. So we are quite okay. I think even in last year, the data shows quite high. Over 100 gigawatt peak has been installed. Last year, I mean the COVID year. COVID is starting year. So still, we are optimistic about the global PV movement or PV activities. Let me show you one of the nuclear scale solar farm. This is in China. Sorry, this is first one in India now. So it has the capacity over 2.25 gigawatt in roughly 57 square kilometer area. If you say about the area, because this area was abandoned, is a desert in Rajasthan. So they are now utilizing it as a solar farm, which has replaced almost 2 nuclear equivalent reactor, okay, which can produce electricity. So this is the achievement. This is second one is China, 2.2 gigawatt. Okay, the third one is India. So it's 2.5 gigawatt, 2.05 gigawatt. So they are, these countries, the India, China, they are coming up, in fact, in very, very enthusiastically coming up with the solar PV. I already shown this one. Let me show the share of the, for example, of thin films, for example, different materials. In 2019, the thin film production was roughly less than 7%, less than 6%. But the number is quite high, 7.5 gigawatt, almost 7.5 gigawatt is a huge amount, at least. The thin films, although it's in research scale, we are doing research yet, but this has also commercialization aspects. Again, I'm going to show you to give you some insights about the R&D about solar cell. For example, I said we need materials, solar cell materials, we need a structure to think of, we need fabrication process to think of, and finally, although we don't think in our stage, in lab, about the economics, because if we think about the economics in our lab, we cannot move on, in fact. That's why let's forget about the economics of the solar cell materials right now. So these three aspects, material, structure, and fabrication process, are the main factors for our young researchers. So important research firms, I have written a many, but mainly silicon solar cells are still most prominent, I should say. They are having the most prospects, but not alone. It is coming up with either amorphous silicon as heat, or it is coming up with perovskite as a tandem structure soon. So if someone wants to do this the research, I think they better concentrate on this tandemization of silicon with anyone else, any other partners, first, second, or third generation. Then the second one is the perovskite, the new material. It is a salt. It was known as a salt, but the prospect of perovskite is huge because it is as same as gallium arsenide in terms of absorption coefficient, absorption ability. Okay, so it has really prospects, but only issue is the stability. Today it gives you 25%, maybe tomorrow it is 0% or less than 5% efficiency. That is the thing that people are now trying to solve, that stability issue of perovskite because of some degradation issues. So prospects of PV R&D for us, we are in Malaysia, or with those who are in developing country, we can do research in three ways. I didn't include the system research today because system research, it needs the software, like how you make the system, PV system, either in a standalone system or grid connected system, or even in a large scale solar farm. So you can play with these softwares, which is free sometimes, and sometimes maybe you have to pay some small amount of money. Then main thing is device and materials research. In device research, you can use many softwares if you do not have a lab facility. And material science research also, you can use many softwares if you don't have the lab facility. For solar cell design research, usually there's a list of the softwares that you can consider. We are doing, in fact, we are also using AMPS and SCAPS, the two, sometimes we do PC1D, etc. So these are the softwares that we use extensively for our understanding of the device behavior before we jump into the fabrication. Then, but research facility is eminent. You need, it's inevitable. In fact, you need research facility, or I should say the kitchen. Okay, you need a kitchen to sustain your home. You know, you have to have a kitchen which has everything, but not like a messy one like this one, or a very poor one like this one. At least a standard one like this one. Okay, these are the some of the kitchens that I took from Google Photos. That needless to say that a good facility is needed, is essential, is inevitable to have good research outcome, to have good food for you. Upon nurturing the chefs, you have to nurture the chefs, also our researchers, to supply good. Also, you have to give them good ingredients to cook good food for you. So that is the thing, analogical thing that. So I'm showing some of the research facility from around the world. For example, this is the research facility in Tokyo Institute of Technology, my alma mater. I did research 5 years there during my master's and PhD, and still I have collaboration with them. I go there, I got a free access. Whenever I go there, I can work for 1 week, 2 weeks, whatever time. So I have, I still work there. And before COVID started, I went there and I made some cell. So you can see the scale of this facility. They have everything under one shed. This is the thing that we need. Everything under one shed, so that you don't have to go out with this, because this is a kind of clean room. So this is in Tokyo Institute of Technology, and then I am showing another one in Europe. This is an EPFL. This is they are getting the highest efficiency in organic solar cell or dye-sensitive solar cell, as well as perovskite solar cell. This Professor Naziruddin is one of the renowned professor in perovskite. So this is the perovskite solar module, a small module he was showing to us. This is the thing that they need, only one room with few very good glow box. So everything in line. So because perovskite, we cannot do it outside. It absorbs the moisture. So the whole room is a clean room, plus the research facility we need is a glow box, so that everything can be transferred within this this evacuated or controlled environment. Okay, so that's why they got over 20% efficiency in perovskite. That is the difference between research facility of their and ours. Okay, so anyway, this is the perovskite solar cell, and then they have also research on the rooftop. They are also measuring the outdoor performance of different kinds of solar panels under that climatic condition. This is also an extra that we are also planning to do in Malaysia in UNITEN. So now let me show some of the research lab I was involved. For example, this is in Bangladesh. This is the Bangladesh Government Research Lab, which in fact they came to Malaysia to UKM when we gave some lecture talk through ISESCO workshop. They saw our thin film lab. They requested us to do the same kind of lab in Bangladesh, and they got huge budget, and they have this lab facility now. They have more good equipments there, and they also can make cells. And I gave my consultancy, I gave my lectures, and still I have some collaboration. They listen to us, they do our things, and we do their things also. But the budget was $7 million back in 2015. I was involved to the university, Chittagong University, my hometown. There's a university for engineering and technology called CHUET, where we got a very low amount of budget, like roughly $600 million. Sorry, 600K, $0.6 million. So we created one lab, and one of the first PhD holder, Professor Amin, he got a PhD from our UKM under this solar cell technology. So his lab now, I also gave my consultancy there. So we have a full-fledged lab, which is 0.6 million, or roughly, I should say, 2.5 million ringgit. Okay, so we have full-fledged things that they can make thin film solar cells. Okay, so this is a good one. But let me show one of the other one that is mind-blowing. In fact, this is also similar kind of university in Rajshahi in the northern part of Bangladesh. Since they do not have the budget, the two professors, this professor, he got his PhD from Japan. So he got all the ideas from Japan, and he created his own equipment, cutting the small pipe, water pipe. This is one of the water supply pipe. He made a small chamber. So, necessity is the key of invention, I should say. So he made thermal evaporation system all from scratch. Okay, so this is the lab I really admire, and I want to show whenever people do not have the money, whatever small money they have, if they have that kind of neck, they can create, and they are now producing masters and PhD from this lab. Okay, our lab already have seen once. This is a Malaysian government initiative, initiated one, Mostly Techno Fund. We got $2 million or 8 million ringgit back in 2008, and which was capable of making solar cell from silicon wafer up to panel. This is the second generation solar cell lab. I think I have already shown you. The setup cost was very low, only I should say 350k ringgit. 350k ringgit is not that much, in fact, and maintenance is very low also, roughly 20k ringgit or 7k US dollar per year. Okay, almost towards the end. What are the limitations in solar PV and how to overcome those limitations in our research? I only talked about the research. I didn't talk about the other space. So our limitations is, in fact, is to improve the solar cell efficiency, first of all, and produce at low cost. So high efficiency, low cost. So it doesn't matter what material we are choosing. It doesn't matter what configurations we are choosing. It doesn't matter what process we are choosing. Final thing is, if we can prove that this material can do high efficiency solar cell, and this configuration can do high efficiency, we don't mind about any dogmatic idea of PN junctions. Maybe PN junctions, it could be any single material kind of, like, Schottky barrier kind of thing. So that's why I have tabulated, I have listed down that where to go, how to revisit the fundamentals of solar PV, and what are the processes or what are the items. So these are the items so far I remember, or I can gather from my literature review. It says that, okay, if we go for multi-junction, as I shown before, or tandem structure, which is very feasible to improve the efficiency, and silicon. In silicon also itself, we can go we can go vertically tandemized structures. It's very, very useful and very feasible. So we can go along with it. Next is graded band gap. Okay, so same material, but you try to change the band gap of the material from window layer towards the back contact, so that the maximum amount of solar energy can be absorbed within the whole bulk of the material. Okay, so this is also feasible, but a little bit complicated, but doable. Then others are, I'm showing some of the things apart from the quantum well, all these things, hot electron cells. This you may hear this kind of, or you may heard of it. Hot carrier electron solar cell, the multi-carrier generations, up and down scale, plasmonics effect, all those things. Okay, these are more futuristic. Okay, in future maybe we can get it, but now it is still questionable. It is still limited by our facilities around the world. Not only, I should say, that our labs, many other labs, they cannot do, unless they have very good lab facilities. They can manipulate electrons by their high spec equipments. Okay, so here I would like to conclude that way forward with solar PV, if you want to go along with solar PV R&D or prospects, or future with the solar PV, some of the things that we have to take away today. First of all, you have to believe that, yeah, people around the world have already taken solar PV or solar photovoltaics as one of their energy generating media or source. So paradigm has shifted enthusiastically from fossil fuel based to PV. And I have some data. In fact, I'm going to show you that in 2019, 26% was from renewables, which includes the water-based one, like the dam one, then hydroelectric one, then also windmill, but also solar PV. Okay, and solar PV has 10% share. Okay, which has produced 727 terawatt hour of energy in 2019 itself. Okay, this is, and which avoided 424 million metric ton of carbon dioxide. So this is a figure. This is a figure that we should say that this is a promising figure to believe in PV. You have to believe in PV. PV is not in just a smaller scale cell that is for calculators or something else, but it is for everything now. It can generate a very good amount of electricity, as same as, for example, those nuclear power stations. Okay, let's jump into the number 3, the further advances. Yes, we have seen many different options are there. So still there are options to do. There are things to do with PV. Material-wise, we can make more materials. Silicon can be researched more in terms of its more promises or prospects. and in terms of its solar cell configuration, in terms of the interfaces, etc. More things can be done in silicon, as well as the second generation solar cells, which are successfully commercialized to date. The number 3 is many novel fronts. I have shown you towards the last of my slides. Okay, so many novel things can be in scenario, but futuristic. If we are not affording those for long-term research, I think better not to touch those. Maybe only the initial things that we learn about their principles through some computer simulation, all those things. It's okay. It's definitely good. But the many novel R&D fronts are open for anyone to come in. But again, there's limitations that we are not well equipped for it to do those research. That's why we are still stuck in our UNITEN or in UCAM. We are stuck with first and second generation and third generations, which are doable. For example, perovskite, we are stuck with that. We didn't touch any of the futuristic materials yet, but there is a huge prospect. With that, I'd like to thank you all for your kind attention, and hopefully you will admit that our goal, our mission is to greenify our Mother Earth with the solar applications by adopting those applications in our lifestyle and being adapted to it. And this is for the future generations, because in future definitely will be shortage of having fossil fuels. So with that, I'd like to conclude my talk. Thank you once again. Thank you, Mr. Zahrul. Back to you.
Thank you, Prof, for all your valuable sharing. It's really amazing technology that converts sunlight into electricity. Fossil fuels are one of the important reasons of global warming, and therefore we must use more and more renewable energy to meet our energy demand. So we are about to the end of our today's session. For your kind information, based on the attendance form, we will send the certificate of participation as early as possible. So now the Q&A session. We got so many questions from our participants. As I can see from the chat box, Prof. Dato, Dr. Kamaruzzaman has already answered so many questions in the comment section. Thank you, Prof. In the meantime, Prof. Lutfi also got some questions to ask. So, Prof. Lutfi, please proceed and mention whom you want to ask.
Yeah, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon again. So, I think I'm not sure whether my question is okay or not. It seems probably trivial because I'm not really into this research. It's about hydrogen, so I'm not sure whether who should I ask this question to?
I think Prof. Kamaruzzaman is the better for hydrogen generation.
Yeah, I guess so. Yeah, I guess so. Prof. Dato Dr. Kamaruzzaman. Yeah, I'm Lutfi. So essentially what I've gathered from your presentation is that hydrogen is very much abundant universally, right? But it's not really something that we can simply get to actually drive our power generation, but it's actually simply a carrier, right, as you have already mentioned. And I've already gathered from your presentation that it's really a challenge to extract this hydrogen, right? And in extracting this hydrogen, you have to have, you have to also use energy in that sense, right? I suppose possibly by using PV, solar, or something like that. So my question is simply, how do you manage in terms of the production of it, and then at the same time you're also facing an issue of storing the hydrogen, especially in mobility industry, right? Automotive. So what do you have to say about this?
Okay, thank you for the question. Very, very interesting question, and we have been talking about hydrogen since my PhD years, about 20 odd years, 30 years ago. My supervisor actually was Professor Nijat Veziroglu, and he's basically a proponent of this hydrogen economy. Yeah, but anyway, technology for production, storing of hydrogen is not new technology. It's technology which is available. And it does make sense when you talk about the hydrogen economy itself. To put it in a nutshell, it is not hydrogen is not the energy source. It is an energy carrier. Basically, what you do is that, like, let's talk about a simple situation where you are in a village. Your energy carrier is actually, when you're a small village, you want to carry your energy. What energy do you carry? You carry your wood. Again, the wood. These are the energy that you can carry. Hydrogen is like that. It's an energy carrier. Therefore, producing hydrogen is an established technology. Transporting hydrogen is a very established technology, and also storing hydrogen is a very established technology. So it is a matter of the economics. It's a matter of if you want to produce hydrogen, it's better to go through the renewable hydrogen path. Mainly of producing the hydrogen from solar, from biomass, from wind, and so forth. But of course, there are challenges in producing this. In terms of storage, you can store hydrogen in terms of compressed storage tank. Of course, you need energy to do it. You can also store in terms of hydrides, metal hydrides, salts, and some salt. So storing hydrogen is not a technology which is not there. It's really there. So the why hydrogen? Because hydrogen is seen to be the the most abundant material on Earth. As you know, before Allah create the Earth, Allah create hydrogen. So hydrogen is there, and also hydrogen can be easily acquired from sources like water. You can split hydrogen into hydrogen and water into water to hydrogen and also oxygen. But coming back to the original question, is the hydrogen economy there? Yeah, it is going to be there. A lot of countries in the world now is producing the hydrogen roadmap for individual countries. We in Malaysia also, we are producing it. So to answer your question, again, you have to think of it as a new paradigm in energy. It is not a source per se, but it is a carrier, energy carrier. Yeah.
Thank you very much. Thank you very much. Mr. Zaro, are you there?
No, it's gone.
Somehow is disconnected.
I have answered many of the questions in the chat.
Yes.
I
think you have Prof. Dato, Doctor, you have Kamaruzzaman, you have already answered almost. So most of the questions I see.
If I can't answer,
but I cannot access to the chat box. Like I don't know which way you use the StreamYard or Prof. Dato. Did you use something else to reply the questions?
You can use a StreamYard.
No,
you have to go to the Facebook. You cannot use the StreamYard.
Okay, that's what I cannot.
While you're talking, I'm looking at book.
You are going to Facebook now. You have the time to use the Facebook.
The 10 minutes back now.
Okay.
Sorry for actually I was out of network.
Okay.
Thank you, Prof.
There's a lot of questions asked concerning the recycling aspect of it. So I've put in the chat a paper that me and also Dr. Nowshad published, the end of life and the possibility for doing doing a program on end of life recycle for especially for photovoltaic silicon solar cell. I think some of it is shown by Prof. Nowshad in his presentation. Is going to be a real issue later on, this recycling business? Because many what do you call it, recycle facilities do include solar panel as hazardous material.
Any questions to me? I cannot, Mr. Zohrul, I cannot answer. I see if you can read out some of the questions, maybe one or two for me, because I have to go to Facebook. I don't open the Facebook and the YouTube channel.
Yeah, there's a question. Yeah.
Okay.
Okay, Prof. I think there is one question to you from Jahangir Hussain.
Okay.
Said while Prob's kite solar cells, including perovskite or silicon
on tandem cells are being.
panels
Well, I
are being
don't understand whether it's a question or while or when. I think it's a when, right?
No, there's no company, right?
No, not yet. I mean, commercialization wise, people are doing still research. Yeah, there is no company, either perovskite or tandem or tandem are being commercialized at the current time. But people are trying. That Oxford University is also trying to establish a lab and also a commercialization facility, and university I think Toledo, I think in there. They're also trying to form, like they're forming groups of 8 universities sometimes, who is strong where, but still nothing came up as a final commercialized product.
Yeah. There are startup company, yes, but not in commercial scale.
No. Okay, should involve circular economy aspect. Yes, definitely. Mr. Park Omar. Yeah, okay, let me read out. I see the question. Should involve circular economy. Yes, circular economy is, yes, production to recycling. So that is the thing, right? So we produce, we use, we recycle and reuse. I mean, these things, definitely, it is already established but it's maybe country-wise. Europe is very strict. Japan is very strict in recycling. So they will penalize you if you do not do recycling of those things. They will penalize you. They will penalize you even for trashing a fridge. If you trash a fridge outside your home, they will penalize you. Definitely, you have to pay the price of recycling to the city office or something like that. So even for the PV panels, there are strict law now. So even I know a company called First Solar, which has the biggest plant in Malaysia. I visited recently. They said starting from, like, they are having a line, like everything, like for example, they get the glass, they make the solar cells, they install it, they monitor it, they collect it, they recycle it. So everything is under one shed now, like under one entity. It's not different parties. Okay, so they have taken the responsibility for the whole. That's why they are still surviving. Even silicon is very strong, but cadmium telluride group, or this company First Solar, is surviving well. They are making more money in thin films because of their strategy. They changed the strategy. Yeah, Oxford PV is trying. Yes, I know. Zamir, Mr. Zamir said Oxford PV is trying. Yeah, everything. But I said that commercially available, you cannot see. Everybody is under this, like they've in the trial, how to make the mini module, for example, from cell to mini module to large module. So there are issues. Okay, so those issues to be solved, because PV is not for one shot. You have to survive, or you have to provide energy for at least 15 years, 20 years, if in case of perovskite. So if there is that issue still, I think these companies, all the startup companies, they are always trying. They're always coming up with new ideas. Even they're making consortium among 8 different universities. I saw in USA recently about the perovskite. So they are making consortiums, everything. So they are pushing money. But as of today, as we know, maybe if it is something happened yesterday, I don't know. But still, as of today, our knowledge says that not some commercial product in the market that you can get. Any other question?
There is another question to Prof. Dato. Could you please share the link to your paper on recycling that was written by you?
I already shared in the chat.
There are so many questions on recycling.
Good business.
So if you have any questions, please write in the comment box. And by this time, I'd like to thank to Associate Prof. Dr. Nowshad Salim, Vice Chair IEEE PES Malaysia, for being host of this program and for her technical assistance to run this program smoothly. There is another question from Farhana Atika. What about broken inverter?
You reset a broken inverter. Inverter is an electronic component. Okay, don't think it's a PV component.
Any electrical device, electronic device.
It's an electronic device. So you recycle it as other electronic devices.
You can get some noble material from any, like you get any noble material from electronic device. The same thing for inverters. I saw a Japanese company, taking some of there's some gold in there, right? Gold or something.
No more, Prof. It was, I mean, when I was studying there in the 90s, they said if you collect 70,000 cell phones, you can get 1 kilogram of gold, because that time the cell phone was using IC that has gold. Wire bonding. So
because
it's 90s.
I did visit recycling of this electronic stuff in
Waste,
Kyoto.
electronic waste. They call it electronic waste
They
recycling.
are mostly collecting those from the PCs. But that was a long time ago. About 10 years ago.
No, that time they used gold, but no more. I mean, if you are talking about the 90s, all the electronics, the IC, they were using gold wire bonding. But nowadays, last 20 years, I should say, they moved to other options because gold is expensive. Anything else, Mr. Zaru?
So, as there is no more question, we'll end our session here. And thank you once again to join our IEEE UPM PES Day Celebration 2021. And we are really overwhelmed to have all participants from more than 30 countries. So I'm really privileged to thank you again. And we invite you to join in the upcoming sessions that you will get from our IEEE PES Malaysia YouTube channel. And please subscribe for the latest information on different topics. So with that, I will include and thank you all the speakers and Prof. Lutfi and Associate Prof. Dr. Rashida and all the participants. So with that, have a good day and thank you.
Thank you so much. Thank you. Assalamualaikum. Very good.
Thank you for inviting me. Thank you.
Thank you, Prof.
Okay.